Under the ERAC G5 standard, harmonic assessment is a mandatory critical path requirement for any new inverter-based connection in the UK. Without a passing report, the project cannot secure a grid connection offer. The challenge is that the distribution grid is never static. Its electrical topology shifts every time a switch flips, a major industrial load cycles, or cloud cover alters the output of nearby solar farms. For Stage 3 assessments, this variability creates a modeling bottleneck. You cannot accurately verify harmonic compliance against a single fixed circuit diagram because the grid itself is constantly changing. Unpredictable events like N1 contingencies, where a primary line is taken out of service, or seasonal demand peaks can drastically shift the network's impedance characteristics. Simulating every physical component of the DNO network under every contingency creates a massive data overhead that exceeds a standard project cycle. The sheer volume of required variables and limited access to real-time utility data makes a manual component-by-component simulation logistically unfeasible. To bypass this complexity, network operators move away from physical modeling. They instead translate these unpredictable behaviors into frequency-dependent mathematical equivalents. DNOs solve the modeling problem by mathematically collapsing the complex upstream network down to a single point, the point of common coupling. This collapsed metric is the equivalent impedance. It represents the grid's combined resistance and reactance as seen from the connection point. This Rx plane provides the coordinate system for mapping the grid's electrical behavior across the entire harmonic frequency spectrum. By utilizing this coordinate system, a vast physical infrastructure is simplified into a manageable mathematical domain. Compliance in G55 Stage 3 is found by navigating this Rx plane rather than just studying physical circuit diagrams. A specific grid scenario, such as the system's fifth harmonic impedance during summer peak demand, is plotted as a single coordinate on the Rx plane. If a major line goes out of service, the impedance shifts, moving to a new coordinate. DNOs simulate thousands of these operating scenarios, plotting every feasible contingency and seasonal variation to capture potential grid behavior. To encapsulate this uncertainty, they draw a bounding envelope around the cluster. This multi-sided polygon is formally called the Harmonic Impedance Locus. The locus defines the absolute range of maximum variation in grid impedance for that specific harmonic order. No matter what happens on the physical network, the actual impedance at any given second is guaranteed to fall somewhere inside this geometric boundary. The locus acts as a stress test tool. It forces engineers to demonstrate that their connection remains compliant across every potential grid state simultaneously. While the locus models the grid, we also need a rigorous model of the generator or storage plant intending to connect. This is the Norton equivalent model, mandatory data provided by the manufacturer. It characterizes the plant's harmonic current injection magnitude and phase for every order. Compliance is determined by calculating the incremental harmonic voltage distortion at the connection point. This is Ohm's law in the frequency domain, the plant's injected current multiplied by the grid's impedance. This calculation is performed individually for every harmonic order in the assessment range. Accuracy is paramount here. If the manufacturer's Norton data is flawed, the entire compliance assessment becomes invalid. G5.5 requires that compliance be proven for the absolute highest distortion point found anywhere on the locus. This requires scanning the entire perimeter of the locus polygon to find the specific coordinate that results in the highest voltage distortion. Engineers are searching specifically for coordinates that indicate parallel resonance. This occurs where the locus shape approaches the horizontal axis, near zero reactance combined with high resistance. At these coordinates, even small harmonic current injections are amplified into large voltage distortions that exceed compliance limits. This stress test approach ensures long-term grid stability across a modern network that is increasingly dominated by power electronics. In many Stage 3 assessments, the impedance data provided by DNOs is a conservative simplification of the actual network. This leads to the use of grouped loci, where several harmonic orders are bundled into a single, massive impedance envelope. The grouping logic assumes the worst-case scenario for the second harmonic could occur simultaneously with the worst case for the seventh. These oversized envelopes often create phantom resonance risks. They suggest a failure at coordinates that do not physically exist on the network. These artificial failures can lead to million-dollar costs for active filter installations that the project may not actually need. A failure against a grouped locus is often a data formatting issue rather than an electrical one. The path to resolution involves requesting ungrouped loci from the DNO, which provides a specific, tighter polygon for each individual harmonic order. This detailed data often reveals that the plant is already compliant, removing the need for physical mitigation. Harmonic loci provide a mathematical boundary for grid uncertainty. Mastering G55 requires treating the grid as a range of bounded mathematical outcomes. Engineers must distinguish between the raw behavior of the system and the mathematical predictions of the model. Navigating Stage 3 connections successfully means understanding the grid as a domain of bounded mathematical possibilities.